So, determine the diameters of a hollow shaft. Diameters of a hollow shaft to sustain a twisting moment that fluctuates between 2.5 kilonewton meter to 1.5 kilonewton meter, together with a bending moment that fluctuates between 2 kilonewton meter to minus 2 kilonewton meter. Okay. Full point. Assume the inner diameter to be 0.6 times outer diameter. Full point. Take normal yield stress as normal yield stress as 400 megapascal, normal endurance stress as 270 megapascal, and factor of safety as 2. Factor of safety as 2. So, now first let us note down the given data. So, maximum twisting moment T max is 2.5 kilonewton meter, okay, and minimum twisting moment is 1.5 kilonewton meter, together with a bending moment. Okay. So, M max is 2 kilonewton meter, okay, and M minimum is minus 2 kilonewton meter. Okay. Now, d I is 0.6 times of d O, sigma y is 400 megapascal, So, sigma E is 270 megapascal and FOS is 2. FOS is 2, right. So, first you find out what is the maximum stress, that is what maximum shear stress due to T max. Okay. Now, in this case, as it is a hollow shaft, so you are going to get a different formula to calculate the polar moment of inertia. Okay. Polar moment of inertia, you are going to get a different formula. Okay. So, similarly, so the moment of inertia, you are going to get a different formula, right. You are going to get a different formula. Okay. So, let us find the value of moment of inertia for hollow shaft. What is the moment of inertia for hollow shaft, and what is the moment of inertia for polar moment of inertia for hollow shaft? You can select the formulas directly from design data handbook, that is what referring chapter number 1. Okay. Chapter number 1. So, otherwise you just recall with I think not uploaded. Okay. So, let us notify here. Okay. So, I will go for first solution. So, moment of inertia for hollow shaft. So, is there anybody know the formula? Okay. So, now substitute d I equal to 0.6 times of d O here. Okay. So, how much you will get? You just calculate. So, I equal to pi by 64 d O to power of 4 minus 0.6 d O to power of 4. How much you will get? Point 6 to power of 4. Okay. 1 minus 0.6 to power of 4. How much?
Zero point zero four seven.
0.047
As 0.47 is
into 2 into divided by 64 is not there.
4 divided by 64 as
What about the value of pi? How much you will get here?
I equal to
I equal to
0.0478, sir.
do to power of 4 divided by,
No, sir. All made, sir. Calculation.
you made everything.
Yes, sir.
Okay. Now, similarly calculate polar moment of inertia. Now we calculate J. How much you got? Zero point 0.09574 divided to power of 4.
Yes, sir.
Right. Next, let us first calculate the equivalent bending stress. Okay. This was sigma B E Q. Okay. So, now to calculate this one, you need sigma m, sigma by sigma E n, okay, into K f into sigma A. So, divided by A B C, right, divided by A B C. So, now let us calculate first the maximum bending stress here. Maximum bending stress, this is what sigma B max equal to, okay. So, M max into y divided by I. Okay. So, now in this case, as this is a hollow shaft, you need to consider the value of I as a separately. Okay. So, now y equal to what? It is d naught by 2, y equal to d naught by 2. That is what you are going to get a maximum bending moment at extreme outer fiber of the element, extreme outer fiber of the member. Okay. So, now let us substitute here. M max is 2 into 10 to the power of 3 into 10 to the power of 3. Okay. So, y is 0.5 d naught, right. So, divided by I is 0.04787 d naught to the power of 4. So, you will get value in terms of d cube. Someone find and say give the value here, sigma B max equal to. Who is rule number 40? Rule number 40.
Yes, sir.
ಎಷ್ಟು ಬರ್ತದೆ sigma B max?
So calculate.
How much you got a sigma B max?
Twenty-three point four. 23.41 into 10 to the power of 6 divided by d cubes. D
23 point, right, right, 23.41 into 10 to the power of 6 divided by d cube. So, let us calculate minimum bending stress here. Minimum bending stress, okay, sigma minimum equal to, okay, this is what m minimum into y divided by I. So, m minimum is minus 2 into 10 to the power of 3 into 10 to the power of 3 into 0.5 d naught, okay. So, divided by 0.04878 d to power of 4, you will get minus 23.41 into 10 to the power of 6 divided by t cube, right. So, now we calculate what is the value of amplitude stress and what is the value of mean stress.
Sir, 20.88 hours, sir.
20.88.
88 into 10 power of 6 hours.
You check it. I think this is the right answer, because you just see here. Now, this is 0.047 here. Okay, you just divide a 0.5 divided by 0. How much you are going to get here?
20.88 was.
20.88. Okay.
Yes, sir.
Now 20.88 here. Okay. Now, so calculate what is the mean stress here. Mean stress equal to what? Sigma B max divided by sigma B minimum divided by 2. So, in this case 20.88. Now, this is what a minus here into 10 to the power of 6 divided by d naught cube minus 20.88 into 10 to the power of 6 divided by d naught cube divided by 2. You will get a value as a 0 here, right. Sorry. So, next to calculate variable or amplitude stress. Okay. This is what sigma B max minus sigma B minimum divided by 2, right. So, 20.88 into 10 to the power of 6 d naught cube, here minus of minus, okay. So, you will get a plus here. So, now this is what sigma m here, okay. Now, this is what sigma A equal to 20.88 into 10 to the power of 6 divided by d naught cube, right. Okay. No. So, what are the other parameters you needed? You needed surface factor, size factor as well as the load factor. Okay. Surface factor, size factor as well as load factor. So, let us assume so load factor A equal to 1, because it is subjected to bending stress, okay, subjected to bending stress. Next, B surface factor, sorry, size factor. So, let us take it as a 0.85 here, and size factor also 0.85. Okay. Now, as they have not specified the stress concentration factor, let us assume the fatigue stress concentration factor kf equal to 1, kf equal to 1. So, now you substitute all values in equivalent bending stress equation. Now, let us substitute. Now, sigma m is you got a 0 here, okay. Sigma y is given, it is 400, okay, 400. Sigma E n is 270, this is 1, this is 1.85 into 0.85 into cube, okay. Here it is a 20.88 into 10 to the power of 6. Now, we will get a value of sigma E q here. Now, this value is in terms of d naught cube. Okay. This value is in terms of d naught cube, right. Is it clear? Now, someone calculate.
42.81 into 10 power 6.
42.81 into 10 to the power of 6. Okay. Now, let us go for equivalent shear stress. Equivalent shear stress. Okay. Now, this is equal to what? Tau m plus tau y divided by tau v n into k f into tau a divided by a b c, right. This is the equation. So, you can refer equations from data handbook and notify the equation number. Okay. That is the best practice. Okay. Now, so let us calculate the maximum shear stress here. So, tau max equal to, okay. So, T max divided by J into R, okay, into R. So, now in this case R is the radius of outer fiber, okay, radius of outer fiber. So, now let us substitute here. So, T max is 2.5, is it right? Okay. So, T max is 2.5 into 10 to the power of 3 into 10 to the power of 3 into 0.5 d naught divided by, you notify the value of J, it is what, 0.09574 into d naught to the power of 4. You will get value of tau max in terms of d naught cube.
.05.
13.05 into 10 to the power of 6, right. Everyone got the same answer? Next,
Yes, sir.
minimum shear stress, okay. This is what tau minimum equal to. So, T minimum divided by J into R So, T minimum is 1.5 into 10 to the power of 3 into 10 to the power of 3 into 0.5 d naught divided by 0.09574 d naught to the power of 4.
Seven 7.8 into 10 power of 6.
How much?
7.8, sir.
Is it right?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So, let us assume here. Okay. Assume load factor A equal to 0.6 because it is subjected to torsional loads, then B has to be same and C also has to be same. Okay. Right. So, now Kf is 1 here, Kf is 1. Now, we need to calculate the mean shear stress, sorry. Okay. So, let us calculate the mean shear stress here, mean shear stress. So, tau m equal to tau max plus tau minimum divided by 2. So, tau max is how much? 13.05 into 10 to the power of 6 divided by d naught cube plus 7.84 into 10 to the power of 6 divided by d naught cube divided by 2.
Ten 10.44 into 10 power of 6.
10.44 into 10 to the power of 6, right?
Yes, sir.
Okay. So, next we go for amplitude shear stress. Amplitude shear stress. So, tau A equal to tau max minus tau minimum divided by 2. This is what 13.05 into 10 to the power of 6 divided by d naught cube minus 7.84 into 10 to the power of 6 divided by d naught cube divided by 2.
Two 2.6 into 10 power of 6.
2.6 into
10 power of 6.
okay. So, now the value of tau y and tau en you must consider here. Okay. So, let us assume here. So, tau y equal to 0.5 times of sigma y. Okay. So, tau en equal to 0.5 times of sigma en. Okay. Now, let us substitute. So, tau equivalent equal to, so tau m plus tau y divided by tau en. Okay. So, kf into tau a b c. So, tau m is how much? It is 10.44 into 10 to the power of 6, okay, divided by d naught cube plus, so tau y it is 135, okay, sorry, 200. I think you are going to get here 0.5 into 400 as a 200, right. So, here 0.5 into 270, it is 135. Okay. So, Kf is 1. Okay. So, tau V A is 2.6 into 10 to the power of 6. Okay. Here it is A is 0.7. Okay, we took a 0.6 here, A equal to, and B equal to 0.85, C equal to 0.85 D naught cube. How much you got?
19.34 into 10 power 6.
19.34 into 10 to the power of 6. Okay. Now, let us calculate diameter of hollow shaft, okay, using maximum normal stress theory. Okay. So, now diameter of shaft. Okay, so, by maximum normal stress theory. So, better refer design data handbook, you notify equation number. So, equation number 2.23 b, okay, 2.23 b. So, what is the equation? So, sigma y by n equal to sigma E q divided by 2 plus 1 by 2 square root of sigma E q square plus tau E q square. So, now sigma y p is so 400 here divided by FOS is 2. Now, how much you got sigma y q? Just add up. How much you got sigma y q? So, 42.81. Okay. So, 42.81 into 10 to the power of 6 divided by 2 into d naught cube, right, plus 1 by 2 square root of 42.81 into 10 to the power of 6 divided by d naught cube, this is square, plus 4 19.34 divided by d naught cube into 10 to the power of 6 square. Now, my suggestion is, so you just take out d naught cube term and outside. Okay. So, it is going to very, I think it is easy to solve the problems if you take d naught cube by outside here. So, let us go for 1 by d naught cube here. Okay. So, now 42.81 divided by 2. I will just rewrite here again plus 1 by 2 42.81 into 10 to the power of 6 square for 19.34 into 10 to the power of 6 square. So, now we calculate what is the value of d naught cube. Then you calculate value of d naught. How much you got a d naught cube?
Eight.
Pardon?
5.58
What 5.58 what?
d cube, sir. D naught cube.
5.58 into 10 to the power of 6.
$73.4 sir. D naught.
73 point d naught. Is it right? So, you go for 74 here, then you notify di 0.6 into 74. So, how much you will get here?
44.4 sir.
44.4 right. Next. So, diameter of shaft by maximum shear stress theory. Next. So, now this is what tau y p, okay. So, divided by n equal to 1 by 2 right. So, now tau y p equal to what? Half of tau y, sorry, half of sigma y. So, now this is how much? 1 by 2 into 400, this is equal to 200 megapascal. Okay. So, let us substitute here. Let us substitute. So, you can take d naught cube outside here, okay, d naught cube outside. So, 42.81 into 10 to the power of 6 is square plus 19.34 into 10 to the power of 6 square, right. So, now we calculate value of d naught cube, then we calculate value of d naught. How much you got? ಎಷ್ಟು ಬಂತು? Everyone silent?
GG is equal to 1048. 1086.
Pardon? Value of d naught. So, you are going to get a plus or minus 2 to 3 mm of this one. Okay. So, you have a 73.4. So, you may get 79 mm or you may get 69 mm. Okay. How much you got?
Sir, 77.
77, right. 77 mm. Okay. Now, how much?
77.7.
77 point.
73.
Okay, then you go for 78 mm. Okay, so now 78 into 0.6 here. How much you got?
36.8.
Okay.
Sir, 40, 46. 46.
Okay, so now I think you got a idea to design the components when they are subjected to the fluctuating loads. Okay, fluctuating loads as well as the combined fluctuating loads. Right. So you have any